This is an example using the Bernoulli equation to find the speed at various points along a pipe. In this case, the water moves through a constricted pipe in steady ideal flow, so that means that we can use all of the assumptions that go with ideal flow, like the Bernoulli equation and the continuity equation are both valid. So we've got water flowing in this pipe. I have marked the pressure and the radius at both the top and the bottom of the pipe, and the top of the pipe is 2.5 meters higher than the bottom of the pipe. The goal is to find the speed of the fluid both at the top and at the bottom. So we want to find V1 and we want to find V2. So since we have two unknowns, we're going to need two equations. But that's okay, we have enough information to use two equations. We have the continuity equation, which just says that the volume of the flow rate of the fluid at one side equals the volume flow rate at the other. So A1, the cross-sectional area of the pipe at the bottom, times V1 equals A2 times V2. That's the continuity equation. And the other equation that we will use will be Bernoulli's equation, which says that the pressure at 1 plus the kinetic energy per unit volume of the fluid at the bottom plus the potential energy per unit volume at the bottom has to equal the pressure at the top plus kinetic energy per unit volume at the top and the potential energy per unit volume at the top. It looks like the other quantity that we need that I haven't written down already, it looks like we're going to need the density of water, and the density of water can be taken to be 1,000 kilograms per cubic meter. So let's start by using the continuity equation, since that's the simple one. It will be easy for us to get V1 in terms of V2 and substitute it into the other equation. So to use the continuity equation, first we need to find the cross-sectional area of each. So the cross-sectional area at 1 is equal to pi r1 squared, which would be 3.14 times r1, which is 2.8 centimeters, but we need to put it in meters so that we're in SI units for everything. So that's 0.028 meters. That's going to be squared. That gives us 2.46 times 10 to the minus 3 square meters. And then area 2 will be pi r2 squared. That's 3.14 times 0.017 meters. We convert that one to meters as well, squared. That gives us 9.08 times 10 to the minus 4 square meters. Then, according to the continuity equation, so to solve for V2, what I can do is divide both sides by A2. So dividing both sides by A2 and putting V2 on the other side gives me V2 equals A1 over A2 times V1. And when you plug in the numbers that we got for A2 and A1, you get that V2 is equal to 2.71 V1. Now it's time to plug that in to the Bernoulli equation, and then we'll have a Bernoulli equation that has only one unknown, and we can solve. So let's plug that in. Everywhere we see a V2, we will plug in 2.7 V1. So that, and I'll go ahead and substitute in the numbers that we have for the variables that are in the Bernoulli equation. So we have P1 is first. We're up here using the Bernoulli equation. So that is P1. P1 was 1.7 times 10 to the 5 Pascal plus 1/2 rho. We can plug in the density of water, 1,000 kilograms per cubic meter, times V1 squared. That's what we're looking for. Plus rho, again, 1,000 kilograms per cubic meter, times G, we'll say is 9.8. H for number 1 was at the bottom, so we'll call that H equals 0. that is equal to, on the other side, P2, which was 1.3 times 10 to the 5 Pascal, plus 1/2 kilograms per cubic meter times V2 squared. Here is where we plug in what we got before for V2. That's 2.71 V1. That is all squared. And then we have the potential energy term, 1,000 kilograms per cubic meter times gravity times the height, and the height at spot 2 is 2.5 meters. So let's plug all of those numbers into our calculator. So I've underlined the left side of the equation in blue and the right side in red so that we can keep better track of which side is which while we're writing these things down. I also have dropped the units because we first, before we drop the units, let's make sure that everything is SI. So we have pascals, that's good. Kilograms and meters, that's good. On the other side, we have kilograms and meters, so we're good. All of the units are SI, so it's okay to drop them, and then we'll end up with an answer that's also in SI. So first term, 1.7 times 10 to the 5, then 1/2 times 1,000 is 500, V1 squared. The potential energy term on the left is 0. And on the right, you get 1.3 times 10 to the 5 Pascal, plus 500, 1/2 times 1,000 is 500, and then you multiply that by 2.7 squared. You get 3.67 times 10 to the 3, V1 squared. And then the potential energy term on the right is 1,000 times 9.8 times 2.5, that's 2.45 times 10 to the 4. Now combining like terms, that gives us 3,145 V1 squared is equal to 15,500. So if we divide both sides by 3145 and take the square root of both sides, we get that V1 is equal to 2.22, and we were careful to make sure that we had SI units in all of our input. That means we're going to get the SI unit of velocity out, which is the meter per second. To get V2, we simply have to use the equation that we got here. So V2 is 2.71 times V1, and that would be 6.02 meters per second. Then to get the volume flow rate is up here. The continuity equation says that the volume flow rate in one end of the pipe equals the volume flow rate at the other end. So we can use either one of those. I will just use A1 times V1. And A1 is 2.46 times 10 to the minus 3 square meters. The velocity at spot 1 is 2.22 meters per second. So you multiply those together, and you get 5.46. And then if you have meters squared and meters, that becomes meters cubed per second. 5.46 cubic meters of water per second flow past each point in that pipe. I kept everything to 3 significant figures. If you are using some software-based homework and you have to be correct to within a couple of percent, it's probably better to pick 4 significant figures. I run out of screen space too quickly if I do that, so I normally don't keep 4, but you can keep 4 all the way through, and you should be right to within a couple of percent at the end if you need to do that for your homework system. That's all. Thanks for watching.